Hello everyone and welcome back to another mini concept, this time about electric fields. So electric fields are regions of space where charges can experience force due to other charges, or just in general, just experience force. And we know that charges interact with each other. So let's put two charges here. Okay. So we'll have two charges. We're not gonna give them any value, we're just gonna give them signs. So we know that between these two charges, there's gonna be an interaction. We know that based on their unlike signs or their unlike polarities, they're going to attract. And specifically, we know that the negative will attract the positive. So we know that much, right? But how do we describe the area between these two charges that actually allow the attraction to happen? Because of that area in space where this charge can experience force, be it attraction or repulsion, as I wrote here, that allows other charges to interact with it. So let's say that I put this charge an infinite distance away. Let's say I put it all the way here. There is a chance that the force that this negative charge would experience is equal to zero. Simply because it's no longer within the region of space where that charge can experience force. So now let's bring it back. That is how we understand and describe electric fields. Now, we have to label some parts as just a set of jargon, perhaps. So, the area that we're trying to measure the electric field with reference to, or the point whose electric field we want to measure, is what we call the source point. And this source point is self-explanatory. This is what emits the electric field. Now we have to determine it using another charge, which can be a test charge or another existing charge. And this is what we call our field point. Field point. So these are our two jargons for electric field problems. So again, to recount, source points are what emit the electric field that we're trying to measure, and field points are the points that are around the source point that allow us to measure the magnitude of the electric field. Now next, before we get on to the problem solving and the math or the formulas, we have to understand how electric fields of various polarities behave. Now, I'm going to make a drawing of something that you might have seen before. However, it's not going to look very nice because I suck at drawing. So I'm just going to make it I'm gonna make it as nice or beautiful as I can. But I'm sorry. Okay? So perhaps we can start by imagining a tube or a wire. And you can also imagine, for example, like maybe that drawing of magnetic fields. But that's for later. You'll understand why. We determined in the last video about Coulomb's law that positive likes to go to negative, right? So basically, we can say that negative charges like having the attention, right? So electric fields around negative charges behave by going towards them. So they go like this. So the electric field around a negative charge, it goes inward. Now, positive is attracted to our negative. So, we can say that it likes to go that direction and it also goes outward instead of inward. So here, it will meet there. This side, it will meet here. This side will meet here. And this side will meet here. It's not a very good drawing, but basically you get the idea. There is a region here where they will essentially just meet. So it will basically go this way, right? And this is what a dipole would look like. A dipole electric field would look like. So the positive electric field goes towards the negative, and the negative electric field goes towards itself. So just so that we have a bit of a cheat sheet here, positive is outward and negative is inward. This is important because exams will actually ask you for the direction of your electric fields. So let's get rid of this mess. And here, now we have this. Let's say now that we want to measure the electric field of a charge. So we'll bring back another charge here. Um, we'll make it. Let's make it a positive as well. Make it a positive so that they're both going outward. They're both going this way. Both going this way. How do we solve for that? Now remember that electric fields are where they can experience force. So we have to derive our formula. Luckily, we ourselves don't have to because there already exists one. The formula for electric field is given by E is equal to K Q over R squared. Now this Q, small q versus big Q, they're not really that different. They both refer to charges, the magnitudes of your charge. And in some sources, you might see that Q is a test charge, but it can also be big Q wherein it's another separate charge. So really, they're just the same thing in this context. Now, electric field can also be solved using another thing, which is another formula, which is F over Q. If you recall from our Coulomb's law rather, F is equal to Coulomb's constant times Q1, or for the sake we'll use Q, small q, Q1, Q2 over R squared. Now, putting that in place of here, basically we'd be getting E is equal to the Coulomb's law times 1 over Q. Now this Q could refer to either of these, so we can cancel one of them out, and we'd end up with the same formula here, which is K to the value of Q over R squared. And now what is the unit for our electric field? The unit for our electric field is Newton per Coulomb. And this makes sense. Why? Because we're trying to see the area of space where charges can experience force. Now, force is distributed based on the charges, right? So the charges itself experiences force, and we want to see exactly how it experiences the force, how to describe the area, right? So the unit is newtons per coulomb. If you want to get a unit analysis, basically we can see that hold on, let's minimize this one. Let's move this here. You can see that the Coulomb's constant, or Coulomb squared, using this we would get rid of the m squared because of the 1 over m squared here. We get rid of this, and from the Q we can get rid of 1 Coulomb. So get rid of that. So now we're left with Newton per Coulomb. Sorry, that might be a bit messy, but I hope that makes sense. See, these two formulas are going to be very important. So I'll get rid of this one at the bottom. Now, back to this problem. Let's say that these two charges are separated only by a meter. Gap between these two is 1 meter. We would solve for them by getting the magnitude of our field point, multiplying it by the Coulomb's constant, and dividing by R squared. So let's say that this is equal to 1 Coulomb, and our Coulomb's constant is equal to 9 times 10 to the power of 9. So using our formula, let's get rid of this. We can get that the electric field between these 2 points would be at the field point rather would be 9 times 1 times 10 to the power of 9 over 1. So in other words, it's going to be equal to 9 times 10 to the power of 9 newtons per coulomb. So that's literally how you solve for electric fields. That's all it is. It's plug and play. However, there are some questions that might be more steps because you might need to derive for certain values. So let's try and practice this formula using our examples. So for our first example, we have A point charge with a charge of 5 microcoulombs is placed at the origin. Calculate the magnitude of the electric field at a point 3 meters away from the charge in a vacuum. Alright, so now we're only dealing with one charge. So basically, let's put our charge here, just smack dab in the middle, just for it to be easier on us. This is positive, and we want to get the magnitude of the charge here, just at a point. And this is going to be 3 meters. Now, let's try plugging in these values into our formula. So we have E is equal to 9 times 10 to the power of 9 times 5 times 10 to the power of negative 6. This is all over 3 squared, which is 9. We can cancel out the 9s, and then we're left with 5 times 10 to the power of 9 times 10 to the power of negative 6. 10 to the power of 9 times 10 to the power of negative 6 follows the rules of exponents. So 9 plus negative 6 is 3. So our final answer is 5 times 10 to the power of 3 newtons per coulomb. And this is the magnitude of the electric field at this point, 3 meters away from the charge in a vacuum. That means that at any point 3 meters away, let's say that these are all 3 meters away, doesn't really matter, that would be the electric field. Now let's explore another question. First is the given. So let's understand the question. Two charges, one being 4 microcoulombs and the other one being negative 3 microcoulombs, are separated by 2 meters. We have to find the net electric field at the midpoint of these two charges. So let's draw the question. We have two charges here. One of them, Q1, let's make this Q1 here. This is positive, so this is plus, and the other one is negative, so this is a minus, and they're separated by 2 meters. So this gap is 2, and you want to get the electric field at the midpoint. So this is 1 meter. This here is 1 meter. There. And we know that the net electric field should basically be going this way, to the right, just because negative attracts positive. So, what do we do from here? So, oops, I forgot to label there. So, we know based on the question that it's supposed to be going to the right. However, we don't know the magnitude or the net electric field at that midpoint. So, what we need to do now is we need to separate our problem into two halves, and then that's when we start working with the numbers. Because once we get both halves, we can start to add them to get the net electric field. So, let's get started with the left side. The left side, our E is equal to, our E is going to be equal to 9 times 10 to the power of 9 times our charge here, which is 4 microcoulombs, all over the distance, which is 1 squared. So this is equal to 36. 9 times 4 is 36. And then law of exponents again. That's equal to 10 to the power of 3. So now for the other side, we're going to do it step by step again with the same formula. So E2 is equal to Coulomb's constant, 9.0, or just 9, times 10 to the power of 9. Sorry, that looks too much like a 4 there. 9 times our absolute value of the magnitude, which is 3, times 10 to the power of negative 6, because micro is equal to to the power of negative 6, all over 1 squared. So here we'll get 9 times 3 is equal to 27, and following the law of exponents again, we'd have 10 to the power of 3. So now from here, we have to determine whether or not we're going to subtract or add these two electric fields. Now we can see that negative fields will have their fields going towards them, and the positive field is also going towards the negative. So both of these fields will actually add up. So we'll have 36 times 10 to the power of 3. Well, let's move this here so I can show more. 36 times 10 to the power of 3. 10 to the power of 3 there. Plus 27 times 10 to the power of 3, which is also equal to factoring out the 10 to the power of 3. Then we're left with 36 plus 27, which is equal to 63. And hold on, let me just move the screen. Our final answer is going to be equal to 63 times 10 to the power of 3, or 6.3 times 10 to the power of 3 newtons per coulomb. And that is our final answer. So again, we combined the fields because they're going in the same direction. However, had they been going in opposite directions, we would need to subtract. So now, on to the last question. So now, a point charge Q, which is equal to negative 2 microcoulombs, creates an electric field. And at what distance from the charge does the electric field have a magnitude of 3000 newtons per coulomb? So here we have a different required to find. We have to look for the distance. Our E, which is 3000, is now equal to 9 times 10 to the power of 9 times 2 times 10 to the power of negative 6 over r squared. This is when we need a little bit of derivation. So, first thing we're going to do is we're going to bring this r squared here, multiply both sides by r squared. So, r squared. This will cancel out. So now we have 3000 r squared is equal to 9 times 10. 9 times 10 to the power of 9 times 2 times 10 to the power of negative 6. Or we can simplify this already and we'll go with 18 times 10 to the power of 3. Now, we're just going to divide both sides by 3000. So over 3000. Over 3000. This is equal to r squared this is basically just adding 3 zeros here. So this is 18,000 over 3,000. And this is going to be equal to 6. We don't want r squared, we want just r. So we get the square root of both sides. So the square root of 6 is approximately equal to 2.449, or for rounding off purposes, 2.5 meters. And that is the distance wherein our point charge has an electric field with a magnitude of 3000 newtons per coulomb. So that's pretty much it. That is all for electric field. And it's important, one of the best takeaways to remember for electric field is how similar it is to the Coulomb's law. And that actually makes it a lot easier to memorize, especially for your exams when you can compare the two, because you can just realize that electric field is just Coulomb's law with only one charge. If you remove one of the charges, you can just get the electric field. That is from Coulomb's law. And of course, if you want to get the force between two charges, just multiply another charge. And it's also important to remember how to get the electric field given the force between two charges. Sadly, we did not have any example for that here, but you can actually do that for this problem here. So give it a try and see if you're going to be able to get the same result. Use the Coulomb's law first, and then get the electric field. So that's all for our in-depth concept on electric fields. Thank you everyone for watching, and I hope you guys learned a lot. And yeah, I'll see you guys in the next video, which is about electric flux. Bye everyone!